Right. Now we'll move on to the application part, which consists of electrical circuits. Application of second or higher order linear differential equations. So in that we have electrical circuits. In this section we'll be considering about the electrical circuits which consists of an active element, that is voltage source, which may be a battery or a generator, and the passive elements like resistance, inductance and capacitance. In this section we consider electric circuits which consists of the active element, that is voltage source, which is either a battery or a generator, and the passive elements like resistance R, inductance denoted with L, and capacitance denoted with C. Right. Now we'll see the relation between the current voltage drop across these three passive elements. Okay, relation between current and voltage drop across the passive elements. The passive elements are resistance, inductance and capacitance. Okay, so consider an electric circuit with a resistance R, inductance L and capacitance C. If T is the rate at which the electricity flows, if T is the rate of flow of electricity, that is I is equal to dq by dt, where q is the charge, or q is equal to integration of I dt, then voltage drop across resistance, is given by ER is equal to IR. Voltage drop across the resistance is denoted with E subscript R, which is equal to IR. And the voltage drop across inductance is given by EL is equal to I into EL is equal to L into di by dt. L into di by dt. And the third is voltage drop across capacitance is given by EC is equal to Q by C, or we can write it as 1 by C integral of I dt. Why? Because Q can be written as integration of I dt. This is regarding the relation between current and voltage drop across the three passive elements. Now we'll see Kirchhoff's laws. Kirchhoff's law states that the algebraic sum of the voltage drops around any closed circuit is equal to the resultant electromotive force in the circuit. It states that first one, the algebraic sum of voltage drop around the closed circuit is equal to the electromotive force E in the circuit. First law states that the algebraic sum of the voltage drop around the closed circuit is equal to the electromotive force E in the circuit. And the second Kirchhoff's law states that the rate at any node, the sum of the inflowing current is equal to the sum of the outflowing current. At any node, the sum of inflowing current is equal to the sum of outflowing current. At any node, the sum of inflowing current is equal to sum of outflowing current. That is given by the Kirchhoff's second law. Now we'll see differential equation of LR, LC and LCR circuits. Differential equation of LR circuit means a circuit which consists of only two passive elements, that is inductance and resistance. Let us consider a circuit with resistance R, inductance L in series with a voltage source E. If I is the current flowing in the circuit at any time t, then by Kirchhoff's first law, algebraic sum of voltage drops around the closed circuit. Yes, we are considering the circuit with resistance R, inductance L in series with a voltage source E. If I is the current flowing in the circuit at any time t, then by the Kirchhoff's law, we can write it as Kirchhoff's law L into di by dt plus I into R is equal to E, right? L into di by dt. Voltage drop across inductance is given by L into di by dt. Voltage drop across the resistance is given by I into R, which is equal to this electromotive force E, as we have written the first law of Kirchhoff's, right? So L into di by dt plus IR is equal to E is the differential equation for the LR circuit, where the resistance and the inductance are connected in series with the electromotive force E, right? So that is like this. This is the resistance R and this is the inductance L. This is the electromotive force with minus plus and the current I flowing in this. So LR circuit. This is LR circuit. In a similar way, we can form LC circuit, RC circuit also, and we can form the differential equations in the same way. Okay. So this is the differential equation of LR circuit. At time t is equal to 0, I will be equal to 0. At time t equal to 0, current flowing will be 0. So by using this, if you observe, this becomes a linear differential equation in I, right? So when we solve this, we'll have some arbitrary constant C. So for removing that arbitrary constant C, you can make use of this condition, that is at time t equal to 0, I equal to 0, we'll get the value of C. We get value of arbitrary constant C from this. Okay. Now we'll write the next one, that is differential equation of LC circuit. Okay, so we know that the voltage drop across inductance is L into di by dt, and voltage drop across the capacitance is Q by C, is equal to the electromotive force E. Right? So one is in terms of I and the other is in terms of Q. So will replace both in terms of q. So I can write it as L into d square q by dt square plus q by c is equal to E, as I is equal to rate of flow of charge or the rate of flow of electricity. I can be written as dq by dt. So I replace I here with dq by dt, then that becomes L into d square q by dt square plus q by c is equal to E, which is a second order linear differential equation in Q. Right? In the similar way, we can write differential equation of RC circuit. That is, voltage drop across R is IR and the voltage drop across C is Q by C, right? Which is equal to the electromotive force E. One is in terms of Q and the other is in terms of I. I'll make this I also in terms of Q. Then I can write it as R into dQ by dt plus Q by C is equal to E, which is again a first order linear differential equation if I move this R to the denominator. Right? So these, first we discussed about the LR circuit, then we took LC circuit, then we have taken RC circuit. Right? So finally we'll see LCR circuit, where we'll have one active element, that is the voltage source E, which is either the generator or the battery, and the three passive elements which are given by resistance, inductance and capacitance. Okay? So differential equation of LCR circuit, which will have all the three elements, right? So we can write this as first with the resistance, then the inductance, then we'll take the capacitance, then we'll take the voltage source minus plus, then the flow of current I. So this is denoted with R, this is denoted with L, and this is denoted with C, and this is E. Alright? So here the resistance, inductance and the capacitance are connected in series with the voltage source E. Okay? Then by the Kirchhoff's first law, voltage drop, sum of the voltage drop around the closed circuit is equal to the electromotive force in that circuit. Right? So therefore, voltage drop across inductance, we have written that as L into di by dt. Voltage drop across resistance, we have written that as IR. And voltage drop across capacitance, we have denoted that with Q by C, is equal to this electromotive force, right? So we can write this completely in terms of charge Q. Then I can write it as L into d square Q by dt square plus R into dQ by dt plus Q by C is equal to E. This becomes a linear differential equation of second order in Q. So I can write it as d square Q by dt square plus R by L into dQ by dt plus Q by LC is equal to E by L, which is a linear differential equation of second order in Q. Okay, it is a differential equation of LCR circuit.